So lastly, I'm just going to show you how to express our the creation and then the annihilation operator, or more the mode Fourier mode functions in terms of the scalar field, because this is we're going to do this exercise in the classical setting, so it's better not to think of these um, as operators. Remember that for the exponential functions, we have the completeness relationship that if I integrate these over all space, sorry, there's a cube, e to the power I, say, k minus k prime x, then this is going to be equal to d cubed, the Dirac delta function of k minus k prime. And this was the normalization condition of plane waves in quantum mechanics. The plane waves, as you know, are not normalizable. So this is kind of a, this was chosen so that the Fourier transform made sense. And this relationship can be thought of as a kind of a continuous limit of the Fourier series orthogonality relationship, where we have a system in a box of length L, then the phases e to the power I, e to the 2 pi I mx by L, where m is an integer, times e to the power minus 2 pi I nx of L, where xn is an integer, is basically just delta mn. So this is just the continuous version of it. Here, m and n are modes, and here k and k prime are continuous modes, or they can be also thought of as momentum. So using this in the expression for our, for a scalar field, which remember is given by phi of x is given by d cubed of k by 2 pi cubed 2 of omega a of k e to the power minus I kx plus a of star of k e to the power I kx. So what we can do is that by multiplying this with the appropriate power of exponential function, so if you multiply it with, say, e to the power minus I k prime x and integrated over d cubed x, then phi of x is going to be given by, so here what we'll have is that, this guy multiplying this guy, and this integral will give rise to a delta function. So let's write that. So d cubed k by 2 pi cubed 2 of omega, and here we have a of, let's say this is omega k. Well, this is assumed to be omega k, so a of k, and then we have e to the power minus I omega prime minus omega t, and then we have a d cubed of k minus k prime. And then we also have another term where we have a star of k here, and then we have the exponential, where now instead of a minus sign between the two omegas, we have a plus sign, and then the delta, the Dirac delta, has in it k plus k prime. So, sorry, so I made a mistake here, because for this to be a relative minus sign here, here's a minus sign here, this needed to be a plus. So we have d cubed of x, and here we have e to the power plus I kx, phi of x, and then we can use this delta function to do the k integral, and then we get 1 over 2 of omega, and here we get a of k. And in the second term, we get a star of minus k, and then we get e to the power minus 2I omega k of t. So similarly, we can show that if you take the transform, the Fourier transform of the time derivative of the scalar field, we get minus I by 2, and then a of k minus a star of minus k e to the power minus 2I omega t. Now we can eliminate a star from these two relationships, and then we get a of k is equal to I times d cubed of k, and then we have e to the power minus I kx, so this is a four-dimensional dot product, and inside we get I times the time derivative of phi of x plus omega times phi of x. So this can be used in deriving the commutation relationship between A and A dagger from the commutation relationship between phi and pi.